We tend to think of computers as inherently brilliant. They process billions of calculations per second. Yet, without a human being giving them precise, step-by-step instructions, that machine remains completely helpless. Computer scientists explain this through the principle of garbage in, garbage out. A machine's output relies entirely on the correctness of the human input. If the logic fed into it is flawed, the result will be flawed, regardless of the processor speed. Take the massive Indian Railway reservation network. It must track hundreds of trains, seating types, and simultaneous bookings from thousands of users across the country at the exact same moment. The computers running it aren't figuring out those logistics themselves. Operating a system of that scale requires abstraction. Before anyone types a single line of code, human beings have to strip away the chaos of the real world and create a pristine, logical model of the problem. Building that logic begins with phase 1, analyzing the problem. We break the situation down into 3 specific components: the exact data we put in, the process required to manipulate it, and the final output we expect to get. Consider taking a broken car to a mechanic. They don't start replacing parts at random. They identify the exact source of a noise and formulate a specific plan of action before picking up a wrench. That plan of action defines phase 2, developing an algorithm. An algorithm is a highly structured recipe, often written in plain language called pseudocode, detailing exactly how to solve the problem. To clearly see how all that logic connects, we translate the text-based pseudocode into a visual language called a flowchart. Flowcharts allow developers to map the flow of control, the precise, undeniable path the computer must take to reach the right answer. This diagram shows the first main way this flow operates: sequence. This is a basic top-to-bottom execution, where the computer handles one step after another, like taking a number, multiplying it by itself, and printing the square. While a straight sequence works for simple math, real-world problems demand intelligent choices. A program usually needs to behave differently depending on the specific data it encounters. That brings us to the second pillar, selection, or branching. Here, a specific condition is evaluated, splitting the logical path based entirely on a true or false outcome. For example, an app verifying a user might check their age. The computer hits the decision point, evaluates the condition, is the age under 13, and routes them down a distinct path to label them a child. The third pillar is repetition, or iteration. Sometimes an action needs to happen over and over indefinitely until a specific condition is finally met. Imagine a while loop set up to accept and add numbers together. It continuously asks for new input, repeating the exact same steps until the user types the number 0 to break the cycle. Sequence, selection, and repetition form the foundational building blocks for every software program currently running on Earth. Once that algorithmic flowchart is mapped out, we reach phase 3, coding. Here, the logical plan is meticulously translated into a complex programming language the machine can actually parse, like Python or C++. But the job isn't done yet. Phase 4 involves testing and debugging, where the program is checked to ensure it handles all possible inputs and catches hidden logical errors. The core challenge of problem-solving lies in ensuring the underlying logic remains flawless under every conceivable condition, making the act of coding the final step of implementation. Consider the stakes when the flow of control is programmed or verified incorrectly in a clinical system. For example, a logical flaw in banking software might cause a system to debit accounts instead of crediting them. In fields like aerospace, a single misplaced decision branch could crash a space shuttle. Faulty algorithms represent structural failures in logic that ripple outward, causing massive, tangible havoc in the real world. The researchers Aho and Ullman summarized this beautifully by noting that computer science is truly a science of abstraction. Computers only execute, they don't think. It remains the human responsibility to build the invisible, logical models that solve the world's problems long before a keyboard is ever touched.